Automatic self-leveling platform for mobile and robotic vehicles. Here's a SketchUp 3D model of what our design is going to look like. It's pretty rough, but it encapsulates the general idea of what our design is supposed to be. As you can see, we have a platform that is attached to 4 servo motors on top of a moving vehicle. The goal with this project is to create a platform leveling machine that when this vehicle goes on different terrains, it's able to keep a platform level so that a load can remain on top of it without sliding off. So what are the objectives of the measurement system? Well, first, it's to maintain a level platform while the car is in changing motion. It's also to detect changes in speed for quick adjustment of the platform if needed. It's to gather and process motion data in real time using LabVIEW, as well as test real-time driver input using a PS2 joystick. So here's another angle of the 3D design. As you can see, we've got 4 servo motors with ball joints attached to the square platform. On these 2 corners of the platform, we've got 2 gyroscopes that measure the changes in angular position, and they tell the servo motors whether they need to lift the platform up and down to keep it level. The ball joints are important because as the platform changes direction and changes orientation, the ball joints allow the panels to flex in and out so they can stay attached to the platform. Sensing mechanisms. Our design requires 3 different sensors to be used at various positions on the device. The first one is a gyroscope that senses rotation by measuring the tiny sideways deflection of a vibrating mass caused by the Coriolis effect. We're going to use 2 of these, and they're both going to be on the square panel on top of the car. The second one is an accelerometer, which detects acceleration by measuring how much a tiny suspended mass shifts when the device moves. That's going to be put on the center of the car to detect the acceleration of the car. Third, a PS2 game joystick, which converts the mechanical tilt of a stick to analog voltage signals using potentiometers. This is going to be the input of the user, and it's going to tell the car which direction and which acceleration to have. Actuation components. We're also going to be using 3 different actuators for this design. The first one is the servo motor. We're going to have 4 servo motors, one on each face of the platform, and it's going to lift and change the orientation of the platform as I discussed earlier. We're also going to have 2 DC motors, and that's going to control the wheels spinning on the front of the car. We're going to be using a tank steering method, which means that each front wheel has a different DC motor attached, and spinning one and stopping the other allows for the car to turn. Spinning both allows it to go straight. We're also going to have a linear actuator, which is going to act as a brake, pressing against the wheel axle on the back wheels and slowing down the car. So let's go through the general flow of the system. First, we got the sensors, which get either environmental or user input. Then it goes to signal conditioning, which amplifies or filters the sensor signals. For example, we'll get the voltage from the accelerometer in volts, and that needs to be converted to meters per second squared. Then we have the data acquisition, which is LabVIEW. LabVIEW reads the data, and it puts it into the control logic. So the control logic is the feedback control system, which, for example, we've got the servo motors on the sides of the platform, and those need to be told the complex math that is involved with raising and lowering the platform the correct amount. That would be the control logic. Then it's actuation. We've got servos and DC motors, which tilt the platform left and right, and which spin the wheels. So yeah, as you can see below here, sensors, signal conditioning, LabVIEW DAC, controller, and actuator. Here are some real-world applications. This technology will be useful in any environment that requires a stable payload on a flatbed that needs to be balanced. This could be in agriculture, it could be on inspection robots on rough terrain, anything that requires a flat platform that must stay level. It can also be used in flatbeds on a truck, smart flatbeds that can make sure that the payload does not move too much. Maybe there's some sensitive material on there that can't be shifted around too much. So there are many areas where this technology will be very useful.